Okay, so can you see the slide?
Yes.
Okay, all right.
Yes, sir. Yes.
Yes, sir.
All right, so before we continue, let's do some revision what we have done. What we have done last week. Okay, so last week I already explained about the introduction of solid mechanics. Okay, so in solid mechanics course, so we are going to analyze the structure. Okay, the analysis that I mean is the stress analysis. Okay, we are going to do the stress analysis. We are going to do the analysis of stress on the structure under load. Okay, under load. So you have structure under load, and then we are going to calculate the stress and also the strain. Okay, so strain represent as a deformation of the structure. Okay, so dalam solid mechanics ni kita akan analyze stress dan juga strain. Okay, stress and also strain pada structure yang dibebani oleh load. Okay, force ataupun force daya. Okay, so there are two type of stress and strain. Okay, we have normal stress and normal strain. And the other one we have shear stress and also shear strain. Okay, so normal stress is developed in the material due to axial force and also bending moment. Okay, so normal stress here, this one, is developed due to axial force and also bending moment. Whereas shear stress, okay, shear stress and also shear strain is developed due to the transverse force and also torsion. Okay, so that's what we have. I have explained last week. Okay, and then as I said, okay, in order to calculate the stress, okay, so the value of force that we will use is the internal force. Okay, so normally in the question they will give you the value of external force. Okay, external force will be given. So what you have to do is you have to do the analysis, static analysis, basically static analysis, in order to calculate the internal force. Okay, and then using the internal force, you can calculate the stress. Okay, so remember, stress is the internal quantity. So in order to calculate the stress, you need the value of internal force. Okay, not external force. Okay, so that is what you have learned also in last week class. Okay, and then I also explain to you because the normal stress and also shear stress come from four different type of load. Okay, come from four different load. Okay, so I explained to you also last week the definition for each force. Okay, so axial force. So I start with the axial force. Okay, axial force where the direction of the force is perpendicular or 90 degree with respect to the cross section area. So that's what we call as an axial force. And then transverse force, I was already explained last week. Transverse force is the force that the direction is parallel. Okay, parallel with respect to the cross section area of the material. And then bending moment. So bending moment is the force where under load, under bending moment, the material is tend to bend. Okay, so when the material tend to bend, so that kind of force we call it as a bending moment. And then the last type of force is the torsion or torque. Okay, so this is the force that cause the material tend to twist. Okay, so when the material is subjected to the force and that material when the material is subjected to force and then the material is tend to twist due to that force, so that force we call it as a torsion. So that's the definition of four different force that will cause dia either normal stress or shear stress. Okay. So today we will start with the before we do the analysis. Okay, so we will start with the equilibrium of deformable body. Okay, as I mentioned last week, strength of material or solid mechanism is dealing with deformable structure or deformable material. Sorry.
Excuse me, sir. Sorry. So, one of my friends waiting for you. Waiting to attend the meeting. Please accept this.
I think I already make auto admit. Let me see. Okay. All right. You can see. Can you see my slide?
Yes, sir.
Okay. All right.
Yes, sir. Yes.
Okay. So basically, I already setting. Anybody can enter the class without my permission, so it should be fine. All right. So as I said last week, solid mechanics is dealing with the deformable body. Means that when the material or the members or the structure is subjected to force, then that material can deform. Okay, deform. Different with static. So normally we assume the structure is rigid, so no deformation. That's why we only do the force analysis, not stress analysis, because we assume that the structure is not deformed. Okay, the structure is rigid. But for solid mechanics, this is more to the real application. In real phenomena, in the real material. Okay, real material basically when it is subjected to the force, then the material will deform. Okay, so that's why because of the deformation, that's why kita akan dapat stress. Okay, that's why kita ada stress pada material tersebut ataupun structure. Okay, so similar to static. Okay, so solid mechanics also will apply the concept of equilibrium. Okay, so the same concept, equilibrium. So static and solid mechanics will apply the concept of equilibrium. What is the equilibrium? Equilibrium means, okay, so equilibrium means the summation of the force. Okay, the summation of the force is equal to 0. Okay, so that is the equilibrium condition. Okay, so all the structure or the material is set under equilibrium condition when the summation of force is equal to 0. Okay, and also the summation of moment equal to 0. Okay, so all the structure must fulfill, okay, these two criteria. Okay, otherwise the structure otherwise we cannot solve the structure using solid mechanics and also static analysis. All right, so what is the summation of force equal to 0? Summation of force equal to 0 means the summation of force in x direction is equal to 0. Okay, summation of force in y direction equal to 0, and also summation of force in z direction equal to 0. Okay, so this is what we call a summation of force equal to 0. Okay, so for the case of two-dimensional, so you have so yang part ni you boleh buang lah kalau two dimension. Okay, kalau three dimension and then all direction, the force in all direction must be equal to 0. Alright. Okay, And then same thing to the summation of moment. Okay, what is the summation of moment equal to 0? It means that the summation of moment about x-axis equal to 0, summation of moment about y-axis equal to 0, and summation of moment about z-axis must equal to 0. Okay, so remember, in solid mechanics, all the structure must fulfill this condition. So otherwise, you cannot solve using the solid mechanics analysis. Alright. Alright, so this is the revision of static. Okay, revision in static. If you have a cable, okay, the structure that you are going to analyze in solid mechanics involve different type of reaction or connection. Okay, that's why we will do some revision on what is the reaction force for each connection, for the connection. Alright, so if you have, let me see whether your friend can enter the class or not. Alright, so this is just revision because kita akan guna banyak kita akan jumpa banyak jenis-jenis connection dalam analysis dalam this subject in this course. So I will I will explain back what you have done in static. Okay, so if you have a cable connection, okay, so you can represent this type of connection using by one reaction force. Okay, if you have cable, so you can represent the cable connection by one single reaction force. Okay, if you have the roller, for example, okay, and then you can represent the roller by also one reaction force. If you have the smooth support, okay, you also can represent this type of connection by one reaction force. Okay, one reaction force with certain angle. Okay, angle here. And then if you have the external pin, okay, you will have a two reaction force, Fx and also Fy. Okay, yang ni you akan jumpa banyak lah dalam solid mechanics. Dalam solid mechanics you akan jumpa banyak this type of connection. And then if you have the internal pin, you also have the X and Y reaction force. Okay, force in Fx and also force in Fy. And if you have the feed support, you will have X, Y and also bending moment M. Okay, so this is all the case for two-dimensional problem. Okay, if, for example, feed support, if you are dealing with three-dimension problem, so you will have Fx, Fy, Fz. Okay, you also have Fz and also you will have bending moment X, bending moment Y and also bending moment Z. Okay, so this is just revision. Okay, now we will proceed with the average normal stress. Okay, normal stress due to the axial load. Okay, due to axial load. So as I said, normal stress, okay, sigma, okay, is developed due to axial load and also bending moment. Okay, bending moment. So if you have axial load, okay, so the normal stress will be developed. If you have bending moment, the normal stress will be developed. Okay, so for this case, for this slide, we will focus on, okay, we will start with the axial load. Okay, what is the normal stress due to axial load? Alright, so this is the example of the material or the member and then subjected to the P, where the P is, if you look at here, okay, the P is 90 degree with respect to the cross section area. So this is what we call as a axial load. Okay, axial load. So when the material is subjected to the axial load, so what happened inside the material, the stress, which is the normal stress, will be developed. Okay, we remember. So what is the normal stress? What is the normal stress due to axial force? The normal stress due to axial force is given by sigma equal to P over A. Okay, P over A. But for this case, you can see here, the sigma equal to N over A. Why N? Because the load is represented by N. Okay, the load is represented by N. So normally, we will represent the load by using the P. So if P, you guna P lah. Okay, kalau dia bagi load tu P, macam ni contoh. Okay, dia bagi P. So stress equal to P over A. Okay, kalau dia bagi load tu N, you letaklah N over A. Okay, N over A. And then basically the sigma equal to P over A. So this is average. This is actually the average normal stress. Okay, why average? Okay, why average? Because when the material is subjected to the load, for example, you have load, you have structure AB, for example, you have structure AB and then subjected to load P. Okay, subjected to load P. So if we look at inside the material, okay, if we do the sectioning, okay, we do the sectioning, so we analyze something like that. Okay, so that is the P. So inside the material, the stress distribution is not uniform. Okay, so the stress distribution in the material is not uniform. Okay, for example here, okay, this is just example. Maybe at the middle, at the center of the material, the value of the stress is slightly higher compared to the outer surface of the material. Okay, so the stress here may be, the value of stress here may be lower than at the center. Okay, but we are not going to analyze in specific location. Okay, so we are interested to calculate the average. Okay, so let's say this is the actual distribution of the stress, okay, which is not uniform. So applying this equation, sigma equal to P over A, we actually calculate the average. Okay, we actually calculate the average stress in the material. So we actually calculate the average. Okay, the average. Okay, so that's why. Okay, I repeat, by using this equation, sigma equal to P over A, so we actually calculate the stress, the average stress. Okay, the average stress in the material. So that's why we put AVG here to represent the average. Okay, but in reality, the stress distribution inside the material is not uniform. Okay, some of the point in the material may have higher stress value compared to other location. Okay, so please remember that one. Okay, and then the stress, okay, as I said, the stress is equal to it's not working. Okay, so as I said, the stress equal to as I said, the stress is equal to P over A, and the stress can be positive or negative. Okay, if the stress is positive, it means that the force that acting in the material, okay, tend to make the material become longer. Okay, so if the force tend to make the structure become shorter, okay, so you will get the stress, you will get the value of stress, negative value of stress. You will get negative value of stress. So it means compression. Okay, so if you get minus stress, okay, minus value of stress, so that's one we call it as a compression. Okay, if you get positive value of stress, that one we call it as a tension. Okay, so stress can be positive or negative, tension or compression. All right, so let's try one example here. Okay, the simplest example. Okay, let's me read the question. The bar has a constant width of 35 mm. So this is the bar. Okay, bar A, B, C, D. Okay, you have bar A, B, C, D, and then the width is 35 mm. Okay, width is 35 mm, which is here. Okay, and the thickness is 10 mm. Okay, so this bar has thickness 10 mm. So it means that the bar is something like this. So imagine this is the bar A, B, C, D, and then the bar has thickness. Okay, the bar has thickness. So the thickness is, okay, the thickness is 10 mm, and okay, dia punya lebar width is 35 mm. Okay, determine the maximum average normal stress. Okay, determine what is the average maximum. Okay, maximum average normal stress, which is the sigma average maximum in the bar when it is subjected to the loading shown. Okay, loading shown. So what we have to do is we have to analyze what is the stress, what is the average stress for each portion of the bar. Okay, for portion AB, for portion BC, and also for portion CD. Okay, sorry, AB, BC, and also CD. Okay, so how to calculate the stress, normal stress, sorry, average stress. So average stress, average normal stress is equal to the P over A. Okay, so let's say you nak calculate stress pada portion AB. Okay, so you tulis average for AB is equal to PAB over AAB. Okay, macam tu. Kalau you nak kira stress pada portion BC, so you tulis sigma average BC is equal to P will be PBC lah, over A will be ABC, something like that. Okay, so how to calculate? Okay, now we can calculate the value AAB. Okay, AAB we can calculate because you are given the width and also the thickness. Okay, so not only AAB, you can calculate the AAB, ABC, and also ACD. Okay, area, cross-section area for each portion you can calculate same, all the same. Thickness 10, and also dia punya lebar adalah 35. Okay, so in order to calculate the stress, what you need is the PAB and also PBC. Okay, and also PDC lah, PCD lah, PCD. Alright, as I said, the stress is the internal quantity. Okay, so in order to calculate the stress, we have to use the internal force. Okay, so how do we determine the internal force? So we have to do the sectioning. You kena potong material tersebut, baru you dapat dia punya internal force. Okay, internal force. Okay, for example, okay, so for example, so this is your bar. Okay, this is your bar. This is A, this is B, this is D, C, and this is D. And then this is 22 kilonewton. This is a 12 kilonewton. Okay, so at B, at point B, okay, so I straight away represent by 9 plus 9. 9 plus 1, 9 is 18. Okay, kilonewton. At point C, 4 plus 4, okay, which is 8 kilonewton. Okay, So in order to calculate the stress for AB, okay, for portion AB, so this is equal to the PAB over AAB. Okay, so what is the PAB? Okay, PAB, you have to do the sectioning at section AB. Okay, you kena potong section AB, and then you boleh pilih sama ada you nak analyze bahagian kiri ini ataupun bahagian kanan of the structure. Okay, so nak mudah you kena ambil bahagian kiri. Okay, so you potong sini, and then you analyze half of the, so dia punya sebahagian daripada structure tu lah. Okay, so for this case you will have something like this. Okay, so that is the 12. Okay, so because you do the sectioning for portion AB, so here you can write PAB. Okay, sebab you potong AB, so you dapat internal force pada portion AB. Okay, so easy. So you can solve this one, this free body diagram. Okay, you can solve this structure. So summation of F in x direction, okay, must be equal to 0. So from here, PAB is equal to 12 kilonewton. Okay, so you get PAB, and PAB is the internal force. Okay, why internal force? Because we do the sectioning and then we see what's the force inside the material. Okay, now in order to calculate the sigma BC, so you need the value of PBC. So what you have to do is you do the sectioning at point BC. So if I draw the free body diagram, so please draw the free body diagram of the structure from the side part or the from the left part or the right part. Okay, so let's say I choose the left part of the structure. Okay, so what I will have is something like this. Okay, so I have 12 kilonewton here. Okay, so AB, here is A, here is B, and here is the sectioning path. Okay, so I have here, I also have at point B, which is 18. Okay, so let me draw, this is 18. Okay, so I have here 18 kilonewton, and here of course because I do the sectioning, so I have here PBC. Okay, PBC. Okay, then I can apply the summation of Fx, okay, is equal to 0. So for this case, 12 plus 18, okay, minus PBC is equal to 0. So PBC is equal to 18 tambah 12 is 30 kilonewton. Okay, 30 kilonewton. Okay, and then last but not least is portion CD. So I do the sectioning at portion CD and then draw the free body diagram. So for this case, I draw the right part of the structure. Okay, because this the left part involve a lot of force, so I choose the simple one, which is the right part of the structure. So I draw the free body diagram. So I have this one, so I draw this part, this one. Okay, so this is a 222 kilonewton, and here is PCD. Okay, PCD. So for this case, using the summation of force in x direction is equal to 0. So PCD is equal to 22 kilonewton. Okay, so now you can see here the maximum internal force is PBC. Okay, PBC. So the stress, the maximum stress that will be developed must be in the portion BC. Okay, so because BC has maximum internal force, so the maximum normal stress that will be developed must be in portion BC. Okay, so we can proceed calculate the stress for portion BC. So I delete the value of force in other portion. Okay. Now the stress for portion BC, okay, is equal to the PBC over ABC. Okay, so the PBC is equal to 30 exponent 3, okay, divide by the area. So the area equal to panjang darab lebar. So kalau you tengok sini adalah, kalau I draw the 3 dimension, okay, so the cross section area must be something like this. Okay, so it's equal to berapa tadi? 0.035 time 0.001 ya, 0.01. Okay, so I convert this one in meter. So you get here, what you get here is 30 exponent 3 divided by 0035 divided by 001. So we get 85.71 megapascal. So that is the sigma average for portion BC, okay, which is the maximum sigma in the structure. All right. Okay, guys, any question?
No, sir.
Easy?
Yeah. Okay, sir.
Okay. So I hope you know how to do the sectioning, okay, and also draw the free body diagram. So that is the simple example. Just now I show you one simple example, so I hope you can understand and follow. Alright, so example number 2. Let me read the question. The structure is designed to support the 30 kilonewton. Okay, so you have the structure like this. Okay, you have the structure A, B, and C. Okay, and C, and this structure support 30 kilonewton. Okay, this structure support 30 kilonewton. The structure consists of boom and rod joined by pin. Zero moment connection at the junction and support. Okay, so the structure consists of boom and rod. So I believe this is the rod, and this is the what we call boom. Okay, boom. All right. Okay, let me add one slide here. Okay. By and rod joined by pin. Okay, so maksudnya adalah, so this boom and also rod is connected, okay, is joined by pin at B and zero moment connection, and at point B there is no moment. Okay, there is no moment at point B. Okay, no moment. Okay, that's mean by zero moment connection. Perform a static analysis to determine the internal force in each structural member and the reaction force at the support. So the question is, determine the internal force in each structural member. Okay, so we have two member, which is member AB and also BC. So what you have to do actually is to calculate what is the PAB and also PBC. Okay, so that is the question. Okay, so internal force for each members. Okay, so means that PAB and also PBC. And the reaction force at the support. Okay, so we also have the support at point C and also point A. So you have also to calculate what is the reaction at point A and also reaction force at A and C. Okay, so that is the support. Okay, so this is the pin support. Okay, so that is the pin support, and here also the pin support. Okay, so I hope you still remember when we have the pin support. Okay, pin support, something like this. So you will have the two reaction force, which is the Fs and also Fy. Okay, so now let's calculate what is the reaction force at A and C and also internal force PAB and also PBC. Okay. Okay, first of all, we have to draw the free body diagram. So let me draw the free body diagram. Okay, so this is the point C, this is the point A, and this is the point B. So at B, we have 30 kilonewton. At point A, because A is the pin support, so you will have AX and also AY. So C is the pin support, so you will have CX and also CY. Okay. Kalau you perhati kat sini ya, kalau you tengok betul-betul kat sini, saya assume all the reaction force in positive direction. Okay, apa maksud positive direction? So normally X positive adalah towards to the right. Okay, towards to the right is positive. So for Y positive, okay, kalau dia directed to the upward, okay, directed ke atas, okay, mengarah ke atas, so yang itu adalah positif. Kalau you perasan sini saya tetap AX positif, okay, follow the direction. AY also positif. CY positif, CX positif, CY positif. So doesn't matter, you can also assume the CX in negative direction, okay, AX in negative direction, but I suggest because we don't know the correct direction, the right direction for the reaction force. So I suggest all of you assume all the reaction is in positive direction. Okay, kalau X dia menuju ke arah kanan, kalau Y dia menuju ke atas. Okay, assume like that. Okay, so and then if you get the value negative value, and then so means that your assumption is wrong. Okay, doesn't matter, the value is still correct, but you know the direction that you assume is wrong. Okay, so please assume all in positive direction. Alright, so okay, let's start with the summation of moment at point C. Okay, let's say in counterclockwise is positive. Okay, so summation of moment at point C, counterclockwise is positive, equal to 0. Okay, so now we are going to calculate the moment at point C. Okay, moment C. So what you have here is AX. Okay, so what is the distance here? 0.8. So distance here is 0.6. Okay, so moment at point C. So AX times 0.6, okay, AX here go to C, so the distance is 0.6, okay, 0.6, positive because here go to C, so it's follow the same direction that we assume, so positive. Okay, and then you have AY is negative 0, CY and CX is 0, doesn't create any moment. And then you have 30 kilonewton, okay, go to C. Okay, go to C. So the distance is 0.8, so plus or minus. So the direction, this direction, is opposite to your assumption, so you get negative. Okay, so you put negative. Erase. So negative 30 times 0.8 equal to 0. Okay, so from here the x equal to, okay, using your calculator, 30, 24 bagi 6, so equal to 40 kilonewton. So that is the AX. Okay, as 40 kilonewton. Positive, so means that your direction, your assumption of the for the direction is correct. Okay, and then you can apply the summation of fx equal to 0. Okay, which is to the right is positive. So here you will have AX, okay, AX plus CX and then what else? No, equal to 0. So CX is equal to minus AX, which is equal to minus 40 kilonewton. So that is the CX. Okay, and then you can apply the summation of Fy. Okay, upward is positive, equal to 0. So for here, for this free body diagram, you can see AY plus CY, and then minus, because the 13 kilonewton is directed downward, so minus 30 equal to 0. So AY plus CY equal to 30. Okay, so you cannot solve this equation, so just leave it. Let's say this is equation 1. Okay, so you need another free body diagram in order to solve this problem. Okay, because you already use the summation of force in x direction, y direction, and also bending moment, but you cannot solve the value of AY and also CY. So what you have to do is you will analyze another free body diagram. Okay, so now let's analyze this AB, so the structure AB. Okay, so let me draw the free body diagram of AB. Okay, for the structure AB. Okay, so that will be the A, and that will be the point B. So let's say this is point B, this is point A. Okay, so let me delete this one first and draw again. Okay, so that is the free body diagram for AB. Okay, here. Okay, so at point A, okay, same thing, you have AX and also AY. So at B you have 30 kilonewton, and you will have the BY, okay, and also BX. Okay, okay guys, my question is, why we have BX and BY here? Why we didn't have BX and BY here? Okay, anyone? Kenapa kita ada BX and also BY kat sini? Free body diagram yang ni. Tapi free body diagram yang ni kita tak ada BX and also BY. Why?
Not have road. Not have road.
Sorry? Rod?
Tak ada road.
Tak ada rod. Okay, tak ada rod. Jawapan lain ada? Ada siapa-siapa nak jawab?
PS Time PY present the rod.
Present the rod. Okay, so the answer is first free body diagram. We draw the overall structure. Okay, we draw the overall structure. So we release the pin from the connection. So at point A, we release the pin. Okay, we release the pin at point A. So once we release the pin, the connection, so you will have AX and also AY. You release the pin at point C, so you have CX and also CY. But at point B, it's still connected. Okay, it's still connected. You didn't release the pin. So that's why there is no BX and also BY. Okay. So for the free body diagram number 2, so we draw the free body diagram of AB. So what we do is, okay, we only draw the free body diagram of member AB. So what we have to do is we have to remove the pin from the connection. So you will have AX and also AY. And then you release the pin at point B because you are going to analyze only AB. So you release from the rod. Okay, you release from the rod. So once you release the pin, you will have BX and also BY. Okay, so that's the reason. Okay, that's the reason. The first one, you didn't release the pin. Okay, you analyze the overall, so you tak cabut pin ni. Okay, that's why dia tak ada BX and Y. So for free body diagram number 2, because you only analyze the portion AB, only member AB, so you should release from CB. Okay, you should release the AB from CB, so that's why you will have BX and also BY. Okay, so please you have to understand that concept, otherwise you cannot, you're not able to draw the right free body diagram. Alright, so from the free body diagram number 2, okay, so we can calculate the moment at point B. So we calculate the moment at point B. So let's say clockwise is positive. Okay, we assume clockwise is positive. So you calculate moment here. So you only have AY. Okay, you only have AY time distance. Distance here is 0.8. Okay, so times 0.8 is equal to 0. So AY equal to 0. Okay, you get AY equal to 0. So from that, you can substitute into 1. Okay, so you substitute value of AY into 1. So we have AY plus CY equal to 30. So CY is equal to 30 kilonewton. Okay, so that is the CY. Alright. What else? We have CX already, AX already, AY, CY. So we have all the value for the reaction force. Okay, remember our question, the question is determine the reaction force at A and C. Okay, so at point A, so means AX and also AY, and for point C means CX and also CY. So we already calculate AX, AY, CX, CY. Now we are going to calculate the PAB and also PBC. Okay. Alright, so let me add one more slide here. Okay. Okay. Okay, now you have AX equal to 40 kilonewton. AX equal to 40 kilonewton. AY equal to 0. CX equal to where is the CX? Okay, CX equal to minus 40 kilonewton, and where's my pen? Okay, so Cy is equal to Cy 30 kilonewton. Okay, so now we are going to calculate what is the PAB and also PBC. Okay, so if we draw the free body diagram again, okay, so here is the CY and also here is the CS, and here is the AY and here is the AS. Okay, then we have 30 kilonewton here. So how to calculate the PAB? As I said, this is the internal force. So this is the AB. So this is the member AB. So what you have to do is you do the sectioning at section AB. So what you will have is, so I analyze the left side. So I analyze the left side here. Okay, so you will have AX and also AY. So here is your PAB. Okay, so if you do the summation of Fx equal to 0, okay, so you'll get PAB, so you will have PAB is equal to minus AX. Okay, so PAB is equal to minus 40 kilonewton. Okay, so PAB actually is in compression. Alright. Now, in order to calculate the PBC, so you have to do the sectioning for member CB. So that will be your PCB. Okay, here saya ambil ni saya ambil ni. Okay, and then you will have CX here and also CY here. Okay, so for this case, because the CX and so CY is not collinear with the member CB, so you have to determine the resultant. Okay, resultant at point C. Okay, so the resultant force at point C is equal to Cy square plus Cx square cert. Okay, so this one equal to 40 square plus 30 square. So RC is equal to 50 kilonewton. Okay, so if I redraw the free body diagram, okay, I will have, this is the PCB and this is the RC. Okay, so CS and CY, we calculate the resultant, so we can replace CS and CY by the resultant force. So for this case, PCB is equal to 50 kilonewton. Okay, so in tension. Alright. Any question?
No, sir.
No.
Okay, sir.
Okay, alright.
Okay, sir.
Alright, so kalau tak ada soalan, okay, let's proceed. Okay, the same question, this one. Okay, the same question. Alright, so now the question is, so the same figure. Okay, now the question is, can the structure safely support the 30 kilonewton load? Okay, given the allowable stress is equal to 165 megapascal. Okay, now the next question is, bolehkah structure, okay, structure ABC tu support 30 kilonewton load okay, which is here, okay, which is this one, okay, given the allowable stress is 165. Okay, maksudnya adakah structure ni boleh support 30 kN ni tanpa fail, okay, tanpa fail. And the allowable stress mean the maximum stress, okay, allowable stress mean the maximum stress that the member can support, the maximum stress, okay, the maximum stress before failure occur, okay. Okay, I repeat again. Soalannya adalah, adakah member ni boleh support 30 kN? Okay, so diberi stress maksimum yang boleh disupport oleh material ni ataupun structure ni adalah 165 megapascal. Okay, so what we have to do is we have to calculate the stress. Okay, the stress for each member, which is the member AB and also member BC, and then compare that stress with the allowable stress. If the stress in the material lower than the allowable stress, means it is safe. Okay, means that the structure is safe. If the stress in the member, okay, in the structure is higher than the allowable stress, so means that the structure actually cannot support 30 kN. Okay, alright. So now we have FAB ataupun PAB lah yang kita kira tadi, kita guna P, tak apa. Okay, and also FBC equal to 50. Okay, FAB equal to 40, FBC equal to 50, ataupun sini PBC. Kita guna tadi P ataupun F, tak kisah. Alright, so let's calculate the stress for member AB. Okay, so stress for member AB is equal to PAB divided by area for AB. Okay, so PAB is equal to 40 kN, 40 exponent 3. So I convert into Newton, divide by the area. Okay, the area for AB. Okay, so the area for AB is given here. Okay, which is 0.03 times 0.05. Okay, so sini you dapat 26.67 megapascal. Okay, so daripada sini you dapat stress pada member AB adalah 26.67. Maksudnya AB selamat. Okay, so kalau you compare dengan allowable, so stress yang AB support, okay, stress pada AB, okay, stress pada AB adalah hanya 26, dan yang dibenarkan adalah 165. So maksudnya AB selamat. Okay, selamat. Kalau you apply 30 kN, AB akan selamat. Okay, now we have to check for member BC. Okay, so sigma BC is equal to PBC over ABC, okay, which is equal to PBC is equal to 50 exponent 3, okay, in Newton, divide by area. So area for BC, area for BC is equal to pi d square over 4, okay, which is equal to 50 exponent 3 divided by pi time diameter is 0.02 over 2 divided by 4. Okay, so sigma BC, okay, using calculator, sigma BC equal to 159 megapascal. Okay, so if you compare with the allowable stress, okay, if you compare with the allowable, okay, if you compare with the allowable stress, so this one is still lower than 165. Okay, sigma BC is lower than 165. Okay, ataupun sigma allowable. So means that member BC also safe. Okay, so means that BC can support 30 kN. Member BC can support load of 30 kN, and member AB also can support the load of 30 kilonewton. So means that the structure is safe. Alright, so next question is, for reason based on cost, weight, ability, and etc. Okay, so there are many uncertainties, there is many factors that you have to consider. So that the choice is made to construct the rod from aluminium. Okay, now this rod, must be constructed from aluminium. Okay, must be constructed from aluminium, where the aluminium have the allowable stress equal to 100 megapascal. Okay, so now we are using the rod. The rod is made from aluminium, and aluminium have the allowable stress of 100 megapascal. So now the question is, what is the choice for the rod diameter? Okay, so if you use 20 mm, kalau you guna 20 mm, so stress pada rod, stress pada rod BC adalah 159. Okay, yang ni kalau you guna tadi 20 mm. Kalau you guna 20 mm, so stress adalah 159. Dan kalau you guna rod diameter yang sama 20 mm, apa yang berlaku? Material akan fail lah, sebab stress dia adalah stress kalau you guna 20 mm dia adalah 159 megapascal, yang mana sigma allowable is only 100 megapascal. Okay, sigma allowable yang dibenarkan, stress yang dibenarkan hanya 100 megapascal, tapi stress kalau you guna 20 mm diameter adalah 159. So maknanya structure ni akan fail. So for this question, okay, what is the diameter? What is the value of diameter that you have to choose so that the structure will not fail? Okay, they will not fail. So for this case, you have to use you have to calculate what is the new diameter that you should choose. Okay, you should choose. Okay, so we have the sigma equal to P over A. Okay, so sigma allowable, okay, is equal to the P BC over A BC. Okay, so from here sigma allowable is only 100 megapascal, so exponent 6 equal to PBC is 50. Okay, 50 exponent 3 divided by ABC. Okay, so we can rewrite this equation. ABC is equal to 50 exponent 3 divided by 100 exponent 6. And from ABC, okay, we can calculate the D. So ABC actually is equal to pi dBc square over 4 is equal to 50 exponent 3 divided by 100 exponent 6. Okay, saya lukis ke atas. So again, pi d square over 4 is equal to 50 exponent 3 over 100 exponent 6. So D for BC is equal to 50 exponent 3 over 100 exponent 6 times 4 divided by pi set. Okay, so I just move 4 to here and then pi to here. Okay, so what you will have is the D. So from this equation, if you solve using calculator, so dBc is equal to 26 mm. So that is the diameter, that's the minimum diameter that you have to use for the rod, so that the stress is lower or equal to 100 megapascal. Okay, so that the structure is safe. Alright, any question?
No, sir.
Okay. Alright. Panjang lagi. Okay. So kalau tak ada, saya rasa kita stop sampai sini dulu. Sebab selepas ni kita akan masuk shear stress lah. Shear stress is different subtopic lah. Alright. So okay. Ada soalan tadi? Tak ada dah? Takkan tak ada tanya soalan.
Ada soalan, sir.
Tak ada?
Nak tanya ada, sir.
Ini siapa ni?
Sir.
Ahmad. Mana tadi? Kalau area kena power of 2, length of arc baru tak perlu 2 pi d pi. Okay, ada soalan daripada Ahmad Ferry ni. Okay, betul lah. So area pi d square over 4. Kalau circumference, okay, ataupun perimeter is 2 pi r. Okay. Alright, kalau tak ada soalan, saya stop kat sini. Kita jumpa hari Rabu. Okay, thank you very much. Okay, see you on Wednesday.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Enggak dia.